Greetings, this is Dr. McGuire, and this is the final screencast for Chapter 16, in which we cover concepts taken from Section 16.3, Introduction to Multiple Regression with Two Predictor Variables. And in this screencast, I have two goals. The first goal is how do you compute the multiple regression analysis using SPSS? And then whenever you compute the multiple regression analysis, you get a lot of output. How do we go about interpreting the output generated from SPSS? So to do this, let's go ahead and turn our attention or focus onto SPSS. And what we want to do is let's use one of the problems at the end of chapter 16. And this happens to be problem 21. And in this problem, we see a bunch of data. There are three variables. So what I want to do is go to the variable view, and I want to create three variables that are named after the variables in this problem. One variable is number of crimes, so I'm just going to put number NO crimes. Keep in mind that when you are naming variables in SPSS, for whatever reason, you can't use spaces, so you kind of have to combine terms. The second variable is amount for prevention, so I'm just going to put amount prev for amount of prevention. And then we have the third variable, which is population size. Now, one of the interesting aspects of SPSS is to make up for the fact that you cannot insert spaces for variable names. You can use spaces in the label. So you can actually go ahead and put in as much detail as you want for your labels. So we will go ahead and write out number of crimes. And then the second variable, amount prevention, is actually amount for prevention. And then the third variable was population size. And so I'm just going to go ahead and write these out. Now, the thing that we have to keep in mind whenever we are putting in information about our variables is we have to let SPSS know what the scale of measurement is for our three variables. And I'm going to go ahead and select scale for all three of these variables. Okay, so this is in the variable view. It's highlighted down here. I'm going to go back to our data view, and I'm going to go ahead and enter in the data. And I'm going to pause for a second, and then when I return, all the data will be entered. So if you're following along, here's a good time to take a pause and then enter in the data. All right, so I have the data entered in for all three variables. And just as a reminder, here is the problem itself. So if we look at problem 21, it says problem 18 in chapter 15 presented data showing the number of crimes, the amount spent on crime prevention, and the population for a set of n equals 12 cities. At that time, we used a partial correlation to evaluate the relationship between the amount spent on crime prevention and the number of crimes. While controlling for population size, it's possible to use multiple regression to accomplish essentially the same purpose. The data are as follows. So I've entered in this data. Part A says find the multiple regression equation for predicting the number of crimes using the amount of time spent on prevention, the amount spent on prevention, and population as the two predictor variables. So amount for prevention and population size, these are our X variables. Our Y variable is number of crimes. So let's return back to SPSS and run the multiple regression. So to do this, we need to go to Analyze, and then we are going to Regression, and we are conducting a linear regression. Now, it's actually called multiple linear regression because we have more than one independent variable. We have two predictor variables, so that's why it's called multiple linear regression. All right, so our dependent variable is actually our criterion variable, and that is the number of crimes. We're predicting, trying to figure out how many crimes is associated with two of our predictor variables, which is amount for prevention and population size. And so I select these two variables and move them over into the independent box. Now once I do that, I'm going to click the statistics button, and then I want to see what all is being provided in our analysis. We're going to get estimates, we're going to get model fit. We want to go ahead and look at descriptives and then part and partial correlations. We're going to click continue, and then we click OK. So really, when you enter the data, it's pretty straightforward. You just need to create different columns for all your variables. Now once you get the output, then it gets a little tricky. So what we see here are our three variables, the means for our three variables, the standard deviations, and the number of observations for each variable, for which we had 12. We also get a correlational matrix, and when we look at this correlational matrix, what we see is the correlation, the Pearson R, for each of our variables. For example, this 0.765 right here, this is the correlation between amount spent for prevention and the number of crimes. So that correlation is 0.765. It's pretty high. For population size and number of crimes, that is 0.933. That's even higher. And so the actual Pearson R's are in this first part of the correlational matrix. Now we also have the significance value, and in this case it is providing us with the significance value if you were running a one-tell test. So the probability of committing a type 1 error is provided for us in terms of a proportion. All of these are less than 0.05, so they're all statistically significant. And then this bottom row just shows us the number of observations per variable. Okay, so now we go to our model summary, and we see that our multiple regression, our multiple correlation, is 0.976. That is huge. And really what this is if we were to take our predicted y's and correlate them with our actual y's, that's what multiple R gives us. Furthermore, if you square that, we get the multiple correlation coefficient of determination. In this case, it's 0.953. And here is our standard error of the estimate, 1.09545. That's a very small standard error. So this model summary gives us an idea of how strong our multiple linear regression equation is. But again, as I pointed out in the previous screencast, we don't know for a fact how strong this is until we conduct an F-test. And so when we look at our ANOVA results, we see the ANOVA is broken down into the sum of squares, and ultimately what we're doing is taking a ratio of the regression mean square and dividing it by the residual mean square. And we get a huge F ratio, 91.333, and it is statistically significant. Now, what I really want to call your attention to down here is the coefficients. So here is a very important table of information. With this table, you can reconstruct the multiple linear regression equation. This right here, the unstandardized coefficients, that is what we've talked about before in terms of, if we were writing y equals mx plus b, mx plus a, this is the information we would use. The other thing to point out is we talked about the standardized regression equation, and in that case you don't worry about a constant. There is no constant. What you worry about is the beta coefficients. And whenever we look at this table here of coefficients, we can see which of these predictor variables is the stronger predictor by looking at the absolute value of the beta coefficients. So we get a 0.8 for amount for prevention, and we also see population size, and that beta is about double the amount or the value for the amount for prevention. So if we were trying to figure out which is the stronger predictor, we'd have to go with the population size because of the standardized beta weight. It's about twice the amount, the absolute value of the amount for prevention. You can also run a hypothesis test for each predictor by itself by running a t-test. And in this case, what we see here is that both of these predictors are significant. We also get our results for the zero order and partial correlations. I would ignore the part correlations because we haven't talked about that, but you will see zero order and partial correlation coefficients as well in this. Now, if we go back to our problem in the text, A says find the multiple regression equation for predicting the number of crimes using the amount spent on prevention and population as the two predictor variables. So how would we go about doing that? Well, we need this table right here. So let's go ahead and copy this table, and then what I'm going to do is paste it into a Word document and kind of walk you through how you would go ahead and create that regression equation. So we are doing predicted y equals, and our constant, oh geez, this is an extremely small constant. It is negative 1.776 to the 15th. I mean, basically our constant is 0. And all right, so when we look at our coefficients, the first thing to point out is that if we were to write the unstandardized multiple linear regression equation, we would want to look at this column here. And in terms of our constant, that is negative 1.776 to the 10 to the negative 15th. Ultimately, we have a constant of 0. So we don't have to put anything down for our constant. However, we do have to put down our slope for the first predictor, amount for prevention, and that is a negative 0.8. Let's see here, let me go back down where I'm supposed to be. Predicted y equals negative 0.8, and we will say x, and then this is one predictor, amount for prevention. I'm just going to put x1 for the time being. Plus, now we need to figure out what our slope is for the second predictor variable, and in this case it's 9. All right, so I'm going to put 9x2, and so there we have our unstandardized regression equation, multiple linear regression equation for this model or for this problem. And if we were to go ahead and write down the standardized multiple regression equation, then we would look at this column. But let's go ahead back and see what the answer is. And sure enough, what we see here is predicted y equals negative 0.8x1 plus 9x2, where x1 is the amount spent on prevention and x2 is the population. Now it asks, find the value of r squared for the regression equation. Well, that's pretty easy. SPSS does that for you automatically. So let's turn to SPSS, the SPSS output again, and look for our r squared. And what we found in SPSS was 0.953. Let's see if that's what we get here for our answer. 0.953. So sure enough, we get what the answer is in SPSS. And how do you interpret multiple r squared? Well, basically what this is telling us is amount or the proportion or the percentage of variability in the y scores. In this case, our y was the number of crimes. How much of that can be accounted for when we know these two predictor variables, amount that we have spent on prevention and population size? Well, since r squared is 0.953, we can say that 95.3% of the variability in the number of crimes can be accounted for when we know information about amount for prevention and population size. Okay, so that does it for this last part of chapter 16. If you have any questions, feel free to follow up with me, and have a good one.